Okay, this is part 2 of the physical versus chemical notes. If you have not watched part 1, go back and watch it and then join us here as we look at the examples. We just left off looking at the law of conservation of mass and what it means about matter that cannot be created or destroyed. And we said the mass of the before, or we call them reactants, has to be equal to the mass after. So we have some particle diagrams here, and we are going to look at each change. Notice they all have a before and after, so they're changes. And we want to determine if they're chemical or physical. Remember that chemical means a reaction happened, bonds broke, or new ones formed. And physical means we've just maybe mixed it up, changed the appearance, the form, the state of matter, the amount, but we didn't actually form a new substance. So let's take a look at our first particle diagram. Before we start any of these, we want to just make sure it follows the law of conservation of mass. When we're drawing particle diagrams, they need to follow. So this is what we mean by following the law of conservation of mass. Check your mass before. We have 5 blue squares in the before. My mass on the after also needs to be 5 blue squares because mass of reactants equals mass of the products. 5. Beautiful. Check the small circles as well. 9 small circles before, 9 small circles after. So this does follow the law of conservation of mass. Each of these will follow the law of conservation of mass. If you don't believe me, you can go through and check and make sure the mass before equals the mass after. There is one particle diagram set that does not, and we will get to that and fix it. Now for chemical or physical. That's what our problem is asking us. Do we have any bonds that formed or broke? Remember, bonds are where the atoms or the shapes touch in our before and after. Did we have any changes in touching of the shapes? No. They've just been mixed. It looks like they've separated into layers. So that would be a physical change. No bonds broken or formed. Underneath it, we have groups of 2. Now we have groups of 2 and a group of 1. Bond broke. Chemical. Top one here in the middle. We have circle square groups and lone circles, and then after we have groups of 3, circle circle square. So it looks like it goes from a mixture to a compound forming new bonds. This would be chemical. Underneath looks a lot like when we just previously did, groups of 2, and now they're all broken into single atoms. Bonds broke. This is chemical. Top. This is the one that does not follow the law of conservation of mass, and it has a note here. Finish the particle diagram so that it follows the law of conservation of mass. Well, let's look at our mass before and fix our after picture so that all of the reactants equal the mass of all the products. We have 6 large circles in the before. In the after, we have only 3. So let's fix that. Let's add in 3 more big circles. You could really put these anywhere you want as long as they're accounted for in the after page. Now let's check the small circles. 12 small circles on the before. Let's check the mass after. 9. We need 3 more. I'm going to put these as little lone dots. And the way that I've drawn this change, we have broken the bond from the little guy to its circle group because it had big circle to 2 little circles. So these bonds here, I broke them, if you will. Oops. Put that back. If we're breaking bonds, then this would be a chemical change. And lastly, before and after, this looks like it was mixed up together. This is a physical change. I don't see any new bonds formed or broken. That is what physical and chemical changes look like on the particle level. Now let's do some macro, kind of zoom out to what we observe in the real world for chemical and physical changes and properties. When we talked in part 1, we said that properties are kind of like a category of something you might observe, whereas changes will describe an actual before and after that occurs. Physical and chemical are going to carry their same meaning. Physical, no reaction required. Chemical, reaction. Remember things to look for if it's a chemical change: heat, light, and energy transfer. Usually that's associated with fire and combustion. Maybe you have bubbles form, you have a color change, maybe a smell, any type of new properties that come with a new substance. And maybe it formed a precipitate or a solid from two liquids that mixed together. So that would be an example of creating new matter, but still following the law of conservation of mass, since the atoms are just forming new bonds or breaking bonds to produce the product. Okay? Keeping that in mind, let's go through these. Just labeling C or P if it's chemical or physical. Logs of wood burn in a campfire. When I see burn, that's telling me reaction. That's chemical. State of matter. Remember we talked about state of matter. If I am observing if something is a solid or a liquid or a gas, does that require a reaction? Nope. Physical. Green mold forms on a slice of bread. When I see mold forming, I see color change, there's a smell that changes, so this seems to me like chemical change. Combustibility. Combustion is a type of reaction involving burning things, so that would be a chemical change. Color. I'm looking at a gray book right now, and it did not require me to do a reaction to observe that. That would be a physical characteristic. Iron is removed from a mixture using a magnet. We did this in lab just last week, and when we did that, it did not require us to break bonds. There was no kind of energy or heat transfer that we observed there. That would be an example of a physical change. Magnetism, in a similar way, physical characteristic. Reactivity with acid. Anything that has to do with a reaction is chemical. So that word reactivity is your sign that you have a reaction going on. Milk goes sour. Well, we've got a precipitate that forms. If you've ever had chunky milk, gross, and it probably smells, tastes different, you probably wouldn't want to drink that. This would be a chemical change. Water freezes to ice. Water as a liquid is same as water as a solid, except for the temperature. But no reaction has occurred. It's still H2O. That's physical change. Clothing is folded and put into a drawer. If I have my shirt in a laundry basket versus my shirt folded in my drawer, it's still my shirt. Physical, no reaction. And boiling point. In order to see if something is boiling, I don't have to do a reaction. It's just something that's happening. I do have to make it change, but that's not a reaction in terms of bonds breaking and forming. So this is also physical characteristic. Now our second part is to underline the properties and star the changes. The best and easiest way to do this is a property looks like a category and a change is more of a description of what happened. And that will always be true. So properties, look for categories. I got state of matter. I've got combustibility. Here, let me get rid of these other underlines so we don't get confused. Okay. Color, magnetism, reactivity, boiling point. Those are properties. The others kind of describe a before and after. Burning, molding, using a magnet, milk souring, water freezing, clothing folded. Those would all be the changes. Changes are usually in kind of the verb form, if you will, and properties are in the noun form. That's just another way to think about it. Properties look like categories of characteristic or observations. Changes describe what happened. use that to help you do the practice problems on the back side. And then also, did I include, oh, I didn't, okay, I'll show you that at co-op. There's a flow chart for properties and changes that we'll look at co-op together, and that should help you also with identifying chemical and physical and kind of putting that all together.